Hi, my name is Benjamin Wilson. This is my video lab report for Physics 2212 Lab 5. As an introduction, the purpose of this lab is to observe and apply Faraday's law by collecting data on a magnet following through a tube of aluminum foil. Some of the foundational concepts relevant to this lab can be seen listed below. And then as a preview of my results, the experimental time that I calculated was 1.302 seconds, and the computational time that I calculated was 1.509 seconds. Models and assumptions. The image on the left depicts the general model for the experimental setup with a bar magnet falling through a tube. Um, in our experiment, it's an aluminum tube. Assumptions that we made were that air resistance is negligible. Gravity and the magnetic force from the aluminum tube are the only forces acting on the magnet. The system is the aluminum tube and magnet, and the surroundings is everything else. And generally speaking, the experiment was as follows. I was tasked with dropping a bar magnet north pole facing downward through an aluminum tube 5 times and recording this descent with my phone, and then I used the video footage to evaluate the amount of time it took the bar magnet to fall through the aluminum tube, and then average those 5 times. That data can be seen collected on the right in the table, and then the relevant measurements of the aluminum tube as well as the bar magnet can be seen depicted on the left. Uh, why can't we use a ferrous tube? For example, steel pipe. Well, a ferrous tube implies that it would contain iron, and iron has magnetic properties. If we were to use a ferrous tube, it would likely be induced into a magnet as a consequence of the bar magnet falling through it, and this would interfere with the falling magnet as well as skew our results. What happens to the magnet? How does this compare to a magnet falling in free space without a tube? Well, the magnet falls slower through the aluminum tube than a magnet falling in free space because a current is induced in the tube that creates an upward magnetic force on the falling magnet. This experiment, in this first slide, we just initialized the physical constants as well as relevant numerical parameters, and also the initialize the plot, the graph, the velocity versus time graph for the falling magnet. This slide shows how we represented the tube as well as the bar magnet in the computation model. This slide shows the two functions that I defined. One being for the magnetic field of a dipole or the bar magnet, specifically relevant to this experiment, as well as the magnetic flux of said bar magnet in the experiment. The code in this slide shows how I calculated the magnetic force of the magnet, or how I calculated the gravitational force on the magnet, as well as the magnetic flux on a ring due to the magnet, and used that information to calculate the induced current in the aluminum tube. And in the final portion of the code for the computation model, I calculated the magnetic force of the magnet on the tube and the magnetic force of the tube and the magnet, calculated the net force present in the system by superposing the magnetic and gravitational force. I calculated the velocity and position of the bar magnet using Newton's second law, and then plotted the velocity versus time graph of the falling bar magnet. Here are screenshots of the computation model. On the left, the representation of the aluminum tube and the bar magnet falling through it. Normally, the blue and the red would be falling through the tube when the model is actually run, and the red represents the North Pole, blue represents the South Pole, and then the graph and relevant data on the right. Questions about this glow strip model. Which color corresponds to clockwise current and which counterclockwise? How can you know? Well, the red corresponds to counterclockwise and blue corresponds to clockwise, and this can be evaluated using Lenz's law. What happens to the dynamics of the system when you flip the magnet around? Generally the same. The magnet will still experience the slowing effect. The only real difference will be that the induced currents will be flipped in the opposite direction. How does the total time in tube of a real world system compare to that of a computational system? How might the computational system be more accurate? Well, although the results are relatively similar, the error can be accounted for the fact that we don't account for air resistance in the computation model, and there's also the potential human error on my side when I was evaluating the measurements of the aluminum tube as well as the bar magnet. So accounting for these, or possibly increasing the number of rings that represent the aluminum tube in the computation model, would increase its accuracy. And then the shape of the velocity versus time plot tells us that the gravitational force and magnetic force are initially unbalanced, but then become balanced for a large portion of the magnet's descent, but then become unbalanced again towards the end as gravitational force overpowers the magnetic force and the magnet falls to the ground. To conclude, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Well, This would cause the current through the conductor to be much greater, due to or can be explained by Ohm's law, and consequently the magnetic force counteracting the downward descent of the magnet would be much greater, possibly stopping it from falling altogether. And if holes or slots were cut into the tube, how would this affect the ring currents in your model? Well, the induced current would consequently be reduced, and the bar magnet would likely fall faster through the tube, as the braking forces would likewise be reduced. Those braking forces being the magnetic force on the descending bar magnet. Thank you.